Right at this very moment, there is a staggering 10 tons of weight pressing down on that innocent-looking glass of water sitting on your desk. Seriously. To put that into perspective, that's roughly the equivalent of two full-grown elephants precariously balancing right on the rim of your cup. Welcome to this explainer, where we're exploring water surface tension, an alternative theory of gravity and pressure. We're basically setting the stage for a mind-bending shift in how we understand everyday physics. Because, well, the standard models we all learned in school, they might not be telling the whole story about what actually holds that water together. 10 tons. That crushing atmospheric pressure is actually the starting point for an entirely alternative theory of surface tension that we're analyzing today. You know, we usually look at a calm glass of water and think of it as just quietly resting there, totally undisturbed, maybe just waiting to quench our thirst. But this source material challenges everything we assume about that placid surface. It asks us to stop looking at the microscopic behavior of the water itself and instead start looking at the massive, invisible, macro forces pressing in from the outside. Okay, let's dive into this. Section 1, the core difference, pulling versus pushing. This is where the scientific debate really heats up. For a long time, we've been taught this very specific narrative about how surface tension works. In the standard theory, we imagine water molecules acting almost like tiny chemical magnets at the surface. They attract each other, bonding tightly, and supposedly pulling together to form this thin, elastic skin. But the alternative theory presented in our source argues something completely different. It suggests water is physically pushed and compressed together to create that tension. It's not some localized microscopic pulling, it's a massive mechanical compression driven by gravity and the physical space the water occupies. And to really grasp the mechanics of this, we need to completely shift our scale. Forget about that tiny glass on your desk for a second. Think about the biggest bodies of water on Earth. I'm talking about the very oceans themselves. Because when you really look at them, oceans are simply giant containers. Section 2, oceans as giant containers and the spatial containment factor. This containment factor is the absolute foundation of this alternative theory. The first pillar is that liquid must fill a closed gap. Whether it's a small container, like a drinking glass, or a natural puddle in a hole in the ground, or massive containers like our deep oceans, the principle is exactly the same. The continents essentially act as giant planetary walls for the oceans. Think about something as vast as the Mariana Trench. It's not just a deep hole. It's the bottom of a planetary basin holding billions of gallons of water captive. Because the water is trapped in this enclosed space with massive walls around it, it has literally nowhere to expand horizontally when external forces push down on it. The liquid is completely contained. Which brings us perfectly to Section 3, compression versus pulling, and gravity's crucial role. So the crucial point is gravity pulls down, the water is forced to compress into its container, and surface tension is born from that physical squashing effect. It's a total shift in perspective. Gravity is the primary engine doing all the heavy lifting here. It pulls the mass of the liquid down against the bottom and against the walls of whatever is holding it. The water is forced to pack tightly together. It's being compressed into the shape of its boundary, kind of like squishing a water balloon against the floor, rather than magically deciding to pull itself together at the molecular level on the surface. If you press a water balloon into the ground, the rubber gets incredibly taut because the water inside is fighting for space. That is the compression effect in action. But how do we actually test this bold claim? Section 4, the lunar crater test, removing the gravity variable. By drastically reducing or even completely removing gravity from the equation, we can see exactly how dependent surface tension is on these massive external forces. Imagine losing that downward pull and transporting ourselves right off the Earth's surface and out into the freezing vacuum of space. Let's move to and see how this builds across completely different environments. Here on Earth, we have high gravity, which translates to high downward compression and therefore high surface tension. Now, travel to a crater on the moon, or just imagine setting our glass of water down on the lunar surface. The gravity is only about 1/6 of what we experience here, which means the water is still enclosed and gravity is still pulling, but the resulting tension on the surface is significantly weaker. Finally, take that enclosed water into a weightless vacuum, an environment with absolutely zero gravity. According to the source material, in a completely weightless space, this form of surface tension simply cannot exist. Without gravity pulling the water down into a container to compress it, the tension completely vanishes. But hey, remember earlier when I mentioned 10 tons? Gravity is really only half the battle. To get the full picture, we have to shift our focus back up to the atmosphere for Section 5, the high-pressure extreme, the weight of the sky. Now, what's really interesting about this slide is the mind-boggling extreme of this theory when we crank that atmospheric pressure all the way up. The air is pressing on the water from above, in the exact same way gravity is pulling it from below. As we discussed, the air resting on top of our typical glass of water creates an atmospheric pressure of roughly 10 tons. It pushes down, heavily adding to the compression created by gravity. But what happens if we multiply that standard pressure to 100 bar? 100 bar is absolutely no joke. That's approximately the pressure you'd feel if you dove 1,000 meters deep into the dark ocean, but applied directly to the surface of our little glass. The source draws a totally shocking conclusion. At 100 bar of air pressure, the water surface must be hard as stone. Let that sink in for a second. The liquid isn't freezing into ice. It's just being squeezed so intensely by the surrounding environment, by the sheer weight of the sky pushing down into the enclosed container, that the surface tension becomes incredibly, impossibly rigid. The physical compression literally turns the surface into a rock-hard barrier. If you were to drop a pebble onto this theoretical glass of water at 100 bar, it wouldn't even make a splash. It might literally just bounce right off.
And this brilliantly illustrates Section 6, the ultimate formula, redefining the surface.
We are completely redefining the surface of water as an interaction of giant macroscopic forces, rather than microscopic internal chemical bonds. Here is the ultimate definition we arrive at, perfectly summarizing our source material. Alternative surface tension is the product of downward gravity acting on an enclosed space, heavily reinforced by atmospheric air pressure. It is an elegant triad of forces. First, you absolutely need the enclosed space, the glass on your desk or the continents bordering the massive oceans. Second, you need gravity actively pulling the liquid down into that restrictive space. And third, you have atmospheric air pressure sealing the deal from above, compressing it all together into what we perceive as a tight surface skin. Take away the walls and the water spills. Take away gravity and the compression lifts. Take away the air pressure and the tension weakens. It's just an incredible way to rethink a basic phenomenon we interact with every single day.
If surface tension is driven by the sheer weight of gravity and the atmosphere pushing down, what other invisible forces are secretly shaping our world from the outside in?